Hey guys, how's it going? So in the video today, we're going to be taking a look at speed calibration control. So this is kind of a follow-up to the last series of videos where we were doing speed control and motor logic. So this is another part of that, which I didn't really talk about, but when you kind of do speed-based programs or speed-based logic, you really need a way to calibrate your speed. So in the video today, we're going to be talking about how to turn your PLC into a speed calibration tool. So without further ado, let's go ahead and get started. So there's a couple different ways that you can do speed calibration on a given motor. One way would be to run the motor at a known speed and check it with a device known as a tachometer. However, in my case, I don't have a tachometer at this time. I plan on getting one a little bit later, but since we have physical hardware that can actually monitor our speed for us, we can essentially turn the machine into a tachometer of its own. So in order to do this, what we're going to be doing is tell the motors to run at a known speed, determine how fast it's rotating based on the input of the various devices, and then with that information we can determine our actual RPM value and adjust our speed control accordingly. So the first thing we do to do this is we need to tell the system what speed we want to run at during the calibration mode. Now, because of the size and the weight of the equipment, it's really easy for the system to go at full speed. So what I've done to make the computation easier is just send the maximum output to the device itself. So in this case, for the indexer, our max speed is 75, and that's in RPM. So when we're doing the calibration mode, we'll change our output speed to the full speed, which is 75. Same thing for the sorting table, but its max speed is 45, so we'll tell the drive to go to 45, and we'll then monitor its speed from the input. I have a few configuration bits to ensure that our calibration mode is available and active. So first bit here is a config bit. This allows the user to do a speed calibration via the HMI, or whatever it means. This means that you have to, or that you are allowed to, do whatever speed calibration mode that is given to you. If this bit's not active, then no speed calibration will be done. The bit here is to indicate whether we're actually in a calibration active mode or not. If we're not, then the speed value is just going to be what the actual auto speed set point is. If we are in calibration mode, we'll send our new value over to our auto speed buffer. So the next thing we want to do is we want to do our speed sample. So in order to do that, we have to monitor a couple different things all at once. The first thing we're going to do is activate our start flag. So you'll have a calibration mode activation bit on the HMI. This will allow the user to begin the calibration sequence. The calibration mode that we're using is going to require the drive to actually move. So in addition, there's going to be a start push button to actually allow the motor to move. Otherwise, we don't want the motor to just kick on. So the user selects to activate calibration, then they press the start button. But we don't want to automatically start monitoring our feedback as soon as the drive comes on. If you think about it, we are still going to have to ramp the speed up to our actual set speed. And until we've reached our set speed, we don't want to start monitoring anything. So the first thing we do is latch this flag bit. In addition, we go ahead and clear any current values that are stored in the system from our last calibration sequence. That way they don't interfere with our current values. The set bit is turned on, this will actually command the motor to start, and we've already given it the speed that we want to run at, so it will begin accelerating. Once it's accelerated, we will have this flag bit, which will be our at speed. Now, we had this in the previous video where we were talking about our motor speed control, where we had flags that would tell us whether we were accelerating, decelerating, or we were at speed or stopped. So this is part of that series of flags. If we're at speed, then this bit will go on. In addition, we also want to wait till we see the first pulse from whatever device it is that we're going to use as our trigger. In this indexer, we're using the proximity sensor that's used as our rotation detection. So when we see that pulse, we can then start our calculation, because if you think about it, if the axis is in the middle of rotation and the sensor isn't quite seeing that flag, then as it rotates, you may get a slightly off reading with this if the sensor isn't seeing the pulse right at the same time. So what we're doing here is we're waiting to start the timer until after we see the pulse from the sensor. Then we'll start the timer and begin counting. So that's what we'll do here. Once we see all these conditions, we'll go ahead and latch the sequence start command, which will begin sampling the speed. To get a good sample, we're going to run the sequence for a full minute. Since the speed is based in RPM, it just seemed like an easy thing to do. So we'll just run it for a full minute, and it will give us our speed command. With each pulse, we'll increment this counter, and this is just a constant accumulation counter. Every time we get a pulse, it'll add 1 to the current value, and then once the timer has completed, or after a full minute of pulses, we will stop counting, and this will be our final count for our rotational speed. When the counter has completed its operation, we can then determine how many pulses there were per revolution and check that against our final speed, or our actual speed measurement. So since we have 4 metal bits on that rotary axis in this particular example, I have this little divisible operation. So basically what this is saying is how many times are we going to see this flag that we're looking for in a given rotation of this axis. In this case there's 4, so I say 4. So that means whatever number of pulses we see, we divide that by 4, and that gives us our total number of rotations per minute. The last thing down here is after the calibration sample is complete, we don't need to necessarily keep the motor running, so we can go ahead and stop the current speed calibration mode. This will stop the motor, and it will also unlatch any other flags that have held this active during this time. Once that is complete, we can then determine whether or not we want to accept those values into the program. In addition to turning off the command during normal functions, we also want to keep in mind that if something happens with the motor as far as a safety-based interference, we obviously aren't going to get a successful speed calibration. So in the event that something happens that forces the motor to fail, we will fault it. Now this is actually a speed calibration fault bit, but this is based on various interlocks that can indicate that the motor is in a failure during the calibration sequence. So that way we won't continue to attempt the calibration mode until or during this fault status. So that's down here, our speed calibration fault detection. In the event that we're doing a speed calibration but we lose our safety interlock, which is right here, then we'll latch a fault. This will stop the speed calibration and will throw an alarm so we won't be mystified by what happened. We'll get an alarm either way, but this way we'll get a secondary alarm saying that not only did the motor fail for some safety reason, but it also has failed the speed calibration and it will not accept any values. This is the rung where we can accept the value. So the idea with this is that the user could then look at the HMI and say, okay, hey, is this a number that makes sense? Do you wish to accept the value? And if the user selects that they do want to accept, we will then change our sample speed into our max output speed. And this is for the SCP instruction that scales our output speed with our real analog output speed. This way our final speed that we command is relatively close to or exactly the same as what we want it to be in reality. So the whole purpose of having speed calibration is to know that you definitely have the axis rotating at the speed that you have designated. If you don't know your relative speed and you're just guessing that it's correct, then you may run into issues when you try to get the axis to move at a specific speed and it can't achieve it because your scaling is off by some order of magnitude. So often in controls, a very good practice is to have a way for the PLC to be given an official actual speed so that what you have in the program matches to reality. Because very often the outside conditions are never always so precise. So this one is for the indexer, but we also have the sorting table motor that we also would want to calibrate. Now for the indexer, we've been using the rotation detection sensor. Now this is a good tool if you only have something like this as a means of input to know when the axis is rotating. However, with the sorting table, we actually have an encoder mounted on the back end of this device. So we can actually use that to our advantage. It's a lot more precise than just simply using a proximity sensor. But we're treating it in this way very similar to a proximity sensor because we only need to know how many times did it make a full revolution each time. There's a couple different ways you could do this with the encoder. You could theoretically do like a speed sample and get like a real RPM value and use the encoder as a real tachometer, but in this case I'm just going to monitor how many revolutions per minute did we do. So that's what we do here. It's the same logic, it's set up exactly the same way, but the only difference is now instead of a input from a singular sensor, we have to look at its relative position. Now the way that I'm handling the encoder in this case is I'm changing its real position to a position in degrees. Because this is a cyclical axis, it will only ever be in a position of 0 to 360 degrees. So I have this limit instruction which will look at our relative position in the encoder, and when our value is between 350, which is our low, remember because below 0 we're going to reset to 360 and down, so 350 is our low and 10 is our high. So as it goes up, we'll have a pulse for that 20 degrees of revolution. We only really need to see it that one instance when it does a one shot, so that's why we have this, but we have a little bit more of a window here so that if there's a scan delay issue that we don't miss a position, primarily because our encoder is handled in our higher priority task, whereas the speed encoder calibration is handled in the continuous non-priority task, so there could be a slight scan delay time, which can result in an error here. So I like to give a little bit of a window because it only really needs to show it for that one pulse. So that's why we have the one shot, but we do need to make sure that we do catch that variation. Once it's actually in position and at speed, we'll then latch the timer, and every time the encoder comes back to see this position, we will increment our counter, and when our counter is complete and we've finished counting for that minute, we will then store our value in our speed sample tag. Since there's only one time that we'll reach this position in the full rotation, we still do the divide, but we just do it once, so it's just divide by 1, and then our output can be stored into our final value for the maximum scale set point. Again, we also have a fail-safe. In the event that the motor fails while we're trying to do the speed sample, we will stop and we will issue an alarm. So now that we've done the review of the program changes, let's go ahead and do some speed samples to see kind of where our speed is at. Is it relatively close to what we expect, or is it actually a little bit out? So let's head over to the bench and check out the motor rotation. So now that I have the program out onto the controller, we're going to go ahead and run the speed test on the indexer first. So since I don't have the HMI running right now, I'm going to go ahead and trigger these manually. So the first thing I'll do is just toggle activation mode for the indexer. And now we'll do a start on the speed. So as you can see, the motor is now running, and we're counting our actual pulses per revolution. It's going to take a minute, so let's run the cycle, and then after it's done, we'll check the result. Alright, so our speed test has completed. We got 299 pulses for a total revolutions per minute of 74.75 revolutions per minute. That was our sampled speed, which is a little bit lower than what our actual max speed was. If you remember, our max speed for that motor was 75. So as you can see, we've got 75 as our original value, and our measured value is 74.75. If I hit accept, it'll move this value into our speed check maximum. So we'll do that. It's stored the value. So as a sanity check, I always like to do the speed test again after doing a recalibration. So what we'll do is we'll again start the calibration mode, and we will start the motor. And we'll do this for another sample time, and then we'll check the result again. Alright, so we've just completed the second speed test. We have the exact same number of pulses for that revolution, and we've got the same speed sample. As you can see, our speed value measured is matching our speed maximum, so there's no point in accepting this calibration because it matches. So based on the information here, it seems that our measured speed is pretty accurate to our actual speed. So that one is pretty good. The next thing we'll do is a speed test on the sorting table drive. I've got an error in my comments. So we'll start a calibration mode for that. Toggle that on, and we'll start it. So we're incrementing our counter, and we're rotating. So let's do a speed sample of this, and when it finishes, we'll check the result. Alright, so our speed test has just completed. So as we can see, our sample count is 45. So that means our speed sample speed was 45 RPM. And so that's our buffer value. And if you look here, we could accept this value, but because 45 is our maximum, we can assume that our relative speed is exactly the same as what we want it to be. So whatever we command is going to be exactly the same RPM. So in addition to this motor calibration logic that we've added, there's a couple more things that I've done to the program since the last time I did a video. So I'm just going to go over that real quick. So one thing I did was changed all the motor tags into a UDT. So as we can see here, I have all of the same tags that we created in previous videos, but rather than having them all in separate tags, to make the program a little bit cleaner, I've made all of the tags into these UDTs. In addition, I've also added the calibration mode tags into this, just like the rest of the motor tags. So everything is all there across the board. It makes the program a little bit easier to create, and if I want to add motors later, all of the tags that we have will be in the other drives as well. And one last thing also, so an additional thing that I added to the motor logic was a smarter calculation for determining our rotation detection alarm timer. So what this is if our speed is greater than 12.5, and I calculated this as being the minimum speed at 12 volts, or 2 volts from the output, because if you remember, the drive will not respond to any value less than 2 volts. So I calculated that on the calculator. 2 volts would be 12.5, so our minimum speed would be that. As long as our minimum speed is greater than 12.5, we will calculate a new preset. The preset is a negative relationship based on our output speed, and I did a little bit of calculations on a piece of paper and stuff to find the correct slope, and all we're doing there is determining our slope factor for our relative time. We're changing that to an integer value in milliseconds, so that's what the multiply by 1,000 is for, and then we add a little bit of a fudge factor, and this is going to allow it to give a little bit more of a buffer of 1.2 seconds, and this will calculate a new timer based on our actual speed. That way the system can be more accurate with a fault timer, and rather than just an arbitrary timer like 2 seconds, it can actually be able to react to the different speed commands of the program. Alright guys, so that's going to do it for this video. I know that was a little bit of a shorter video, and it wasn't really that full of information. I've actually got a bit of a work trip coming up, so this was really the only time I had to make a video. But I wanted to make sure there was at least something out there that was educational and informative. So I hope you guys enjoyed that video. It was a pretty interesting way of understanding how to create calibration logic for your program to help get your speed settings as accurate as possible. If you have any questions about the video, I'd like to hear from you. You can leave a comment down below. And if you like videos like this and you want to see more videos, I highly encourage you to hit the subscribe button. And if you haven't checked out the motor logic videos, I'd highly encourage you to check those out. I'll put a card up if you want to check those out. I highly encourage you to do that. There's a lot of very informative and educational information in there. Anyway guys, I hope to see you on the next video. Thanks for watching. Bye.